All right, so this section is about some word problems, some applications of exponential growth and decay. We've already talked about it a little bit, but we're going to be able to solve different kinds of problems now that we know about logarithms. So we are going to be talking about things that have this form, right? So we have some initial value, some initial amount 0 at time 0, times e to the kt. Okay, so all the equations we're going to be thinking about have this form. So things that have continuous growth or decay. So populations, radioactive decay, things like that. Okay, so let's just remind ourselves what these graphs might look like. So here is this equation where a is 2, k is 3, and what's this going to look like? Well, this is going to be exponential growth. And it's going to cross the y-axis at the a0 here at 2, right? Whatever that coefficient is. And at 1/3, when x is 1/3, this is e to the first power, and the y value is 2e, right? How about this? We have a negative exponent, so we have exponential decay, right? So again, it crosses the y-axis at 3, at 0, 3, and this point is going to be at 1/2. It'll be at 1/2, it'll be 3 over e. Okay. So here's just a summary of all of those things. We kind of have 3 critical points or key points on our graphs. The domain in both cases is -infinity to infinity. The range is 0 to infinity. There's no x-intercept. There's a horizontal asymptote at y equals 0. The y-intercept in both cases is at a0. And it's increasing if k is greater than 0 and decreasing if k is less than 0. All right, so let's do a few examples. We have a population of bacteria that doubles every hour. If the culture started with 10 bacteria, graph the population as a function of time. All right, so what do we know? It's a bacteria, it's doubling every hour, and its initial value is 10. We just started with 10 bacteria. So our A0 value is going to be 10, right? All right. So what else do we know? Well, we know it doubles every hour. Okay, so at time 0, there were 10. So they don't give us a second point, but we can figure it out because it doubles every hour. So after 1 hour, how many bacteria are there? 20, right? So we can plug in, we can create our own point, 120, right, to plug into our general equation. Our A0 is 10, e to the kt. So our t value is 1, our y value is 20. We divide through and get 2 equals e to the k. We use our skills from the last section we can take the natural log of both sides and get natural log of 2 equals k, right? So now we know k. So yes, here we go. Our k is natural log of 2. So y equals our initial value times e to the kt, where k is natural log of 2. And what is e to the natural log of 2? Well, they are inverses, right? So that's just 2. So we would get this equation here. And we can graph that. It crosses the y-intercept is at 10. It's going to be exponential growth. At time 1, we know that it's 20, right? So here could be a second point, and we could connect the graph like that. All right, so let's talk about half-life. So things that have half-lives that are often described with half-lives are radioactive decay, right? You can see here about like the half-life of carbon-14 or uranium, I don't know what it is, 256 or something. The half-life of radioactive elements, right? They decay at a constant rate over time. So sometimes we'll know the half-life. So how can we figure things out if we know the half-life? Well, so the half-life, so when the half-life happens, we have half as much as we started with. It doesn't matter how much. If we started with 100, we'll have 50. If we started with 10, we'll have 5. If we started with 20, we'll have 10, right? So the question is, if we want to find the half-life, okay, if we want to solve for the half-life of a radioactive element, okay, what is that going to be? Well, when at the half-life, when T equals the half-life, how much do we have? We have half of what we started with. If A0 is what we started with, now we have half of that, right? It doesn't matter how much we started with, and that's good because that divides out, right? We're left with 1/2 equals e to the kt. We take the natural log of both sides. We could rewrite this as negative natural log of 2 or leave it as natural log of 1/2. These are equivalent using properties of log or using, properties of logarithms and exponents, right? Think about that. And so we can solve for t, okay? Negative natural log of 2 over k is going to be our half-life. So let's try to use this. So they tell us the half-life of carbon-14 is 5,730 years. Express the amount of carbon-14 remaining as a function of time t. Okay, so let's think about how we do this. So here's our original equation. A equals A0 e to the kt. Okay? All of our equations in this section, all of our questions, we're starting with this equation. After 5,730 years, how much is left? Half of whatever we started with, right? This is the half-life. Okay? So we can divide by A0. It doesn't matter what that is. It could be a lot, it could be a little. We divide by it and we're left with 0.5 equals e to the 5,730 times k. Let's take the natural log of both sides and we can solve for k, right? It's the natural log of 1/2 divided by 5,730. So there's our k value. Here's our equation, right? A equals our original amount times e to the natural log of 1/2 over 5,730 times t. Okay. What about doubling time? What if instead of half-life, we have doubling time? Well, everything's going to be the same, except now instead of 1/2, we're going to have 2. Right? We do the same thing. We divide everything by A0, take the natural log of both sides, we solve for t, and we get natural log of 2 over k. So here's a different kind of thing. So this isn't an actual law, a physical law, but you might have heard of Moore's law. So I think he hypothesized this like in the 70s or 80s. He just noticed that the doubling time for the number of transistors that can be put on a computer chip is approximately 2 years. So he noticed about every 2 years, computer scientists were able to put like double the amount of transistors onto a computer chip. So there's no reason to think that will like hold for all time, right? But they just wanted to mix it up a little bit and not make you do a radioactive decay. Okay, give a function that describes this behavior. So we're going to pretend that this is always true, that the doubling time for these number of transistors is 2 years. So what's that going to look like? Well, we start with this, right? If the doubling time is 2, then k is going to be the natural log of 2 over 2. And we would just plug that in for k into our original equation. Okay. I'll be honest, I would not memorize this. Okay. I would just figure this out every time, because then you don't have to worry if it's doubling time or tripling time or half-life. Okay. It's going to be the same process every time. I would just rederive it to get your final equation. Okay. So those are some examples of the kinds of equations you're going to be solving here. Remember, we are always starting with things of, well, not with this, but A equals A naught e to the kt. Okay, so hopefully that'll get you started, and let me know if you have questions.